we have here, going back to rotating objects, I have an object here that has a certain velocity, v, and it's going around with angular velocity omega, and a little later the angle has increased by an amount theta, and then the velocity is here. We may now do something we haven't done before. We could give this object in this circle an acceleration. So we don't have to keep the speed constant. Now v equals omega r, so that equals theta dot times r. And I can take now the first derivative of this, then I get a tangential acceleration, which would be omega dot times r, which is theta double dot times r, and we call theta double dot, we call this alpha, and alpha is the angular acceleration, which is in radians per second squared. Do not confuse ever a tangential acceleration, which is along the circumference, with a centripetal acceleration. The two are both there, of course. This is the one that makes the speed change along the circumference. If we compare our knowledge of the past of linear motion, and we want to transfer it now to circular motion, then you can use all your equations from the past if you convert x to theta, v to omega, and a to alpha. And the well-known equations that I'm sure you remember can then all be used. For instance, the equation x equals x0 plus v0 t plus 1/2 at squared simply becomes, for circular motion, theta equals theta 0 plus omega 0 t plus 1/2 alpha t squared. It's that simple. Omega 0 is then the angular velocity at time t equals 0. And theta 0 is the angle at time t equals 0 relative to some reference point. And the velocity was v0 plus at. That now becomes that the velocity goes to angular velocity omega equals omega 0 plus alpha t. So there's really not much added in terms of remembering equations. If I have a rotating disk, I can ask myself the question now, which we have never done before, what kind of kinetic energy, how much kinetic energy is there in a rotating disk? We only dealt with linear motions, with 1/2 mv squared, which we never considered rotating objects and the energy that they contain. So let's work on that a little. I have here a disk, and the center of the disk is C, and this disk is rotating with angular velocity omega that could change in time. And the disk has a mass m, and the disk has a radius r. And I want to know at this moment how much kinetic energy of rotation is stored in that disk. I take a little mass element here, m of I, and this radius equals r of I, and the kinetic energy of that element I alone equals 1/2 m of I times v of I squared, and v of I is this velocity, this angle is 90 degrees, this is v of I. Now v equals omega r, that always holds for these rotating objects, and so I prefer to write this as 1/2 m of I omega squared r of I squared. The nice thing about writing it this way is that omega, the angular velocity, is the same for all points of the disk, whereas the velocity is not. Because the velocity of a point very close to the center is very low. The velocity here is very high. And so by going to omega, we don't have that problem anymore. So what is now the kinetic energy of rotation of the disk, the entire disk? So we have to make a summation. And so that is omega squared over 2 times the sum of m of I Ri squared over all these elements Mi, which each have their individual radii Ry. And this now is what we call the moment of inertia I. Don't confuse that with impulse, has nothing to do with impulse. And this is moment of inertia. So the moment of inertia is the sum of M, I, Ri squared. So this can also be written as 1/2 I put a C there, you will see shortly why, because the moment of inertia depends on which axis of rotation I choose, times omega squared. And when you see that equation, you say, hey, that looks quite similar to 1/2 mv squared. And so I add to this list now, if you go from linear motions to rotational motions, you should change the mass in your linear motion to the moment of inertia in your rotational motion, and then you get back to your 1/2 mv squared. You can see that. So we now have a way of calculating the kinetic energy of rotation, provided that we know how to calculate the moment of inertia. Well, the moment of inertia is a boring job. It's no physics. It's pure math. And I'm not going to do that for you. It's some integral. And if the object is nicely symmetric, in general, you can do that. In this case, for the disk, which is rotating about an axis through the center, and the axis that's important is perpendicular to the disk, that's essential. In that case, the moment of inertia equals 1/2 m times r squared. And I don't even want you to remember this. There are tables in books and you look these things up. I don't remember that. I may remember it for one day, but then obviously you forget that very quickly again. Needless to say that the moment of inertia depends on what kind of object you have. Whether you have a disk or whether you have a sphere or whether you have a rod makes all the difference. And what also makes a difference about which axis you rotate the object. If we had a sphere, a solid sphere, then, so here you have a solid sphere, and I rotate it about an axis through its center. Then the moment of inertia, I happen to remember, equals 2/5 mr squared, if r is the radius and m is the mass of the sphere. My research is in astrophysics. I deal with stars, and stars have rotational kinetic energy. We'll get back to that in a minute. Not in a minute, but today. And this is the one moment of inertia that I do remember. If you have a rod, and you let this rod rotate about an axis through the center, and this axis is perpendicular to the rod, the latter is important, perpendicular to the rod, and it has length L, and it has mass m, then the moment of inertia, which I looked up this morning, I would never remember that, equals 1/12 ml squared. And all these moments of inertia you can find in tables in your book on page 309. So the moment of inertia for rotation about this axis of a solid disk is 1/2 mr squared. But it's completely different, the moment of inertia, if you rotated it about this axis. So you take the plane of the disk, instead of rotating it this way, you rotate it now this way. You get a totally different moment of inertia. And most of those you can find in tables. But not all of them. Tables only go so far. And that is why I want to discuss with you two theorems which will help you to find moments of inertia in most cases. Suppose we have a rotating disk, and I will make you see the disk now with depth. So this is a disk, and we just discussed the rotation about the center of mass, and I call this axis L. And so it was rotating like this, and it was perpendicular to the disk. This is the moment of inertia. But now I'm going to drill a hole here, and I have here an axis, L prime, which is parallel to that one. And I'm going to force this object to rotate about that axis. I can always do that. I can drill a hole, have an axle, nicely frictionless bearing, and I can force it to rotate about that. What now is the moment of inertia? If I know the moment of inertia, then I know how much rotational kinetic energy there is. That's 1/2 I omega squared. And now there is a theorem which I will not prove, but it's very easy to prove, and that is called the parallel axis theorem. And that says that the moment of inertia of rotation about L prime, provided that L prime is parallel to L, is the moment of inertia when the object rotates about an axis L through the center of mass plus the mass of the disk times the distance d squared. So this is the mass. And that's a very easy thing to apply. And that allows you now, in many cases, to find the moment of inertia in situations which are not very symmetric. Imagine that you had to do this mathematically, that you actually had to do an integration of all these elements mi from this point on. That would be a complete headache. In fact, I wouldn't even know how to do that. So it's great, once you have demonstrated, once you have proven that this parallel axis theorem works, then of course you can always use it to your advantage. Notice that the moment of inertia for rotation about this axis, which is not through the center of mass, is always larger than the one through the center. You see, you have this md squared. It's always larger. There is a second theorem, which sometimes comes in handy, and that only works when you deal with very thin objects. And that is called the perpendicular axis theorem. If you have some kind of a crazy object, which of course we will never give you, we always give you a square or we give you a disk, but it has to be a thin plate, otherwise the perpendicular axis theorem doesn't work. And suppose I'm rotating it about an axis perpendicular to the blackboard through that point. I call that the z-axis. It's sticking out to you. That's the positive z-axis. I can draw now any xy axis where I please at 90-degree angles, anywhere in the plane of the blackboard. So I pick one here, I call this x, and I pick one here, and I call that y. So z is pointing towards you. Remember, I always choose a positive right-handed coordinate system. My x cross y is always in the direction of z. I always do that. And so you see that here, x cross y equals z. Now you can rotate this thin plate about this axis. You can also rotate it about that axis. And you can also rotate it about the z-axis. And then the perpendicular axis theorem, which your book proves in just a few lines, tells you that the moment of inertia for rotation about this axis here is the same as the moment of inertia for rotation about x plus the moment of inertia for rotation about the axis y. And this allows you to sometimes, in combination with the parallel axis theorem, to find moments of inertia in case that you have thin plates which rotate about axes perpendicular to the plate, or sometimes not even perpendicular. Sometimes you can use, if you know this and you know this, then you can find that. So both are useful, and in assignment 7, I'll give you a simple problem so that you can apply the perpendicular axis theorem. There are applications where energy is temporarily stored in a rotating disk, and we call those disks flywheels. And the rotational kinetic energy can be consumed then at a later time. So it's very economical. And this rotational kinetic energy can then be perhaps converted into electricity or in other forms of energy. And there are really remarkably inventive and intriguing ideas on how this can be done. Of course, whether it is practical depends always on dollars and cents, and to what extent it is economically feasible. But I have always, even when I was a small boy, I remember when I was 7 years, it already occurred to me that all this heat that is produced when cars slam their brakes, all you're doing is you produce heat. You lose all that kinetic energy of your linear motion, whether somehow that couldn't be used in a more effective way. And this is what I want to discuss with you now and see where we stand. This is actually being taken seriously by the Department of Energy. So I want to work out with you a an example of a car which is in the mountains and which is going to go downhill. And the mountains are very dangerous, zigzag roads, and so he or she can only go very slowly. And the maximum speed that the person could use is at most 10 miles per hour without killing him or herself, which is about 4 meters per second. So here's your car. And let's assume you start out with 0 speed, and let's assume that the mass of the car, will give it nice numbers, is just 1,000 kilograms. And so you zigzag down this road. Let us assume that the height difference, h, let's give it a number, 500 meters. And you arrive here at point P, and you later have to go back up again. What is your kinetic energy when you reach point P? Well, you have a speed of 4 meters per second.